Everybody can have a seat. We'll go ahead and get started. I'd like to thank everybody for coming to the last program of the year. I think we've had a great program year with the different activities we've had. We've had different dinner meetings. We've had a couple workshops. I think we've had a very successful year. So wanted to end the year off on another great topic at a great location. I think everybody here is going to enjoy it. The presenter is Mr. Brion Hurley. We were talking at the dinner table tonight. I've known Brion since he started working at Rockwell Collins. He sat across from on the other side of the cubicle from me. So that was about 12, 13 years ago, quite a while ago. Time really flies by. So again, I've worked with Brion a long time. I got a lot of respect for Brion. Brion came to us, came to Rockwell from University of Iowa, got his master's in quality management and productivity. The guy knows more about stats than probably anybody else I know. So he can make that stuff do all kinds of things, I guess. But Brian's going to talk to us this evening about regression analysis. Kind of a funny story about that. Wanted to do something on black belts and Six Sigma and everything this evening. And I talked to Brion about it, and he suggested regression analysis. And I said, okay, that sounds good. Why don't you write up a summary on your presentation so we can put that in the newsletter. So Brion writes something up and sends it to me. And I said, Brion, you got to write it for people that aren't black belts or statisticians or whatever, something that pretty much anybody can understand, you know. And he said, well, I kind of think I did that. And I said, thought about it for a second. I said, Brion, you got to write it so I can understand it. And then he understood it, so he wrote it and sent it back to me, and that's what we put in the newsletter. So, again, I've known Brion a long time. So I'm going to turn the presentation over to Brion, and hopefully everybody's going to enjoy the presentation and walk away with a better appreciation for regression analysis. And Brian's also going to highlight some real-world examples of how he's successfully been able to use it at Rockwell Collins and some other places. So I'm going to turn it over to Brion Hurley.
Thanks, everyone. Can you hear me okay? Okay, so what I wanted to cover tonight is not get into a whole lot of detail on regression, but really try to frame it in a way that is get you thinking about application and where to apply it to maybe some issues or problems you're working on and you run across. So I'm going to try to walk through pretty slowly through the concept, try to, again, ease you into it, and then we'll touch on a few of the concepts here, but if you're looking for a detailed analysis class, it's not probably what I'm going to provide. If you have some questions, we can try to answer those at the end. I'll look to some of the other experts in the room I know that are here that can help answer some questions. It does get pretty technical. And so there is a lot of information and a lot of assumptions to look at and a lot of things to check and make sure. So I don't want to make it seem like it's simple, but I don't want to scare people off saying, well, that's just too complex, I can't do that on my own. So I hope at the end of this you feel comfortable at least take the first couple steps and figure out where you can apply it and maybe do some quick analysis and then try to get some help with making sure you really got all your analysis squared away. Okay? And if you have questions, feel free to stop me and let me know. I think I'm going to try to pack it full of content. Oops.
Clicker might not work. You might have to do it the old-fashioned way, Brian.
Can you change it to DOE?
Or at least a 5Y.
Yeah.
5Y.
So let's start with a little quiz question for you.
Okay. Oh, I wonder this.
How much does Dave Berger make a year in salary? Now, don't blurt out anything right away. I want you to think about this a little bit. I'm going to give you just one guess at it. So does anyone want to start off with a guess? I've got the right answer too, so. No one's going to take a guess? 105,000. Okay. Anyone else? 110. Okay. This is like the Price is Right. I'm not saying no higher or lower. No.
Behind door 3. Does this include his ASQ salary?
Yes. Yes, it does. That might change your answer, I'm sure.
Oh, then, yeah, drop it to 95.
With expenses and. Yep. Any other good guesses? No? Okay. So pretty tight there. So why did you guess what you did? And what kind of questions come in your mind about Dave? Is it the way he handles himself? Say, that guy's got to be making a lot of money. Just the way he dresses. Tall? Okay, tall and the jacket. All right.
I look kind of starved.
He doesn't eat well.
Skinny? All right. These are very important factors on predicting salary. What else? What other things would you, let's say you didn't know Dave at all. What are some of the questions you would want to ask before you made some kind of guess on his salary?
Where do you work?
Where do you work? Okay. What else?
What do you do?
Education, job position. Good. What else?
Where do you live?
Where does he live? Okay.
Experience.
What he drives?
What was that?
What he drives?
Oh, what he drives. I won't tell a lot. What was the one back there?
You go, Dave?
Experience? How many years of experience he has in the job or in his job title? Yeah.
How much
Okay.
jewelry his wife has?
All right, these are very good predictors. More than I thought. So probably, I said 14 years with the company. So that's going to factor into your decision a little bit. Did you know he was the executive VP of marketing? Does that change your guess a little bit?
He just knows a lot of good people.
That's right. So that might
Did
change
say he
your
is
guess a
or he
little bit.
was?
He is. You didn't know
He is.
that about Dave? Yeah, lots of information here. He's been there 8 years in that role. He's only 30 years old. That's pretty amazing too.
He started when he was 16.
That's right. So he's probably been building up quite a bit on his bank accounts. How about performance review? Actually didn't go so well. He kind of got a 2 out of, we have a 5-point scale at Rockwell.
Is he a friend of yours?
Was.
Maybe after the presentation we should ask him. He has a bachelor's degree in art, if you didn't know that. Master's degree in physical education. Is this changing your guess on his, what other, so the other factors, you guys threw out some really good ones. You know, maybe the job conditions, maybe the benefits package of Rockwell, maybe that's not all included there. Someone said where he lives, so the state, you know, if this is in California versus Iowa, other factors there. So, okay, Dave, give out the right information here. 125,000 from Rockwell as a salary, 33,000 from ASQ, president. So we're kind of undershooting his salary there on our guesses. All right, so a lot of these factors come into play, and that's, you know, initially you might take some quick guesses, but if you were basing your decision on how close you could get, you might want to consider some of those other factors before you make your guess on his salary. So how about home prices? Same kind of thing. How do you predict the price of a home? So let's say that this community we're looking at has a median price of $300,000. So if we use that number, and that's the only information we have, that might be our first starting point for guessing at what another house might cost in that area, knowing nothing else about that home. But within that community, the houses really vary between 150,000 and 500,000. So if you were to make a guess on that, you know, there is some variability there. What other information would you want to know about the house to make that prediction?
Square footage.
How big it is, square footage,
Age.
age, number of floors,
How much land?
how much land, okay?
How much their neighbors sold their house for.
Okay, yeah, maybe it's community price,
Even location within the community.
Appraisal.
location,
Tax assessments.
tax assessments, okay. So if we were having like a brand new house going in there, yeah, we could use maybe some similar size. And what would those be based upon? Kind of a lot of things we talked about. Maybe there's some other amenities. Talked about the age, number of bedrooms, garage size, maybe distance from a downtown or some other landmark. Some other features, landscaping, the neighborhood, that type of thing. So lots of different factors that come into play. So let's just start with one. Just say we don't know anything else, but we can start with a factor and try to see how does that relate to what I'm trying to predict or look at in my data. So if selling price is something you want to know, then let's pick one like square footage, is pretty common, as a predictor and see how it matches up. And we can use a scatter plot to compare the two. So we've got the selling price, the number that we're most concerned about, and then we plot that against our square footage. And we'll look to see what is the pattern that is created from there. And you can see the red dots indicate different homes. So this is a 1,500 square foot home for $130,000. And here is a 3,500 square foot home for almost $400,000. So if you look at it, you can see that definitely the square footage has something to do with the selling price. Definitely a factor that we want to know if we're trying to predict that. If we had just picked the average, you can see that that's going to vary quite a bit. We could be pretty far off if we didn't know what the square footage was. So just guessing the average or the middle of my data is probably not going to be very accurate, even though that's the most, you know, it's right in the middle. You'd be pretty far off. So if you had a 2,200 square foot home, it'd be around $225,000. If you just picked the average, you would have been saying $300,000. So that's a pretty big difference there. So it's good to understand what are those other factors that go into this. So in regression analysis, who has had some experience with this before? Handful of you, okay, good. So when we talk about regression, we're kind of looking at two main ones that I'll talk about. There's a lot of other techniques, but the first one is just a simple linear regression. That's kind of what I showed. It was one output, which is the selling price, versus one input, and that was the square footage. So we're just kind of doing a one-to-one comparison there and saying, if I know the square footage, how well does that tell me the sell price? Multiple linear regression is obviously more variables, and that's where we use more than just square footage. We take some of these other factors and see how they fit in and how they help predict that number. So if we had, let's say, 5 data points on this sample, one thing we're trying to do is try to draw a line that kind of connects the dots through there as best as we can, and that's this best fit or least squares method. So if we, again, kind of pick the average of those data points, it's going to be somewhere below 5. That's their scale over here. So this is kind of our average point. That doesn't really fit very well to the numbers, to the plot here. But that's where our average starts out with. So if we didn't have any factors that came into play, then we probably have to pick our average. And what we're trying to measure is how far from the line are the data points in reality, because that's going to tell us how good our model is. And the further away the points are from the line, the worse our model is for predicting that. So that looks like that's not really that good. So maybe we look at a different slope of that line. And it looks like it fits a little bit better. There's still quite a bit of difference between that dotted line and the actual data point. So basically what we're doing with this best fit is trying to match it up so get a little bit closer. And then ultimately we find one where those differences are as small as we can get. And that's kind of the best line that would fit right through there. And that's kind of where we're going to look to create our model of what this relationship is. That's the line of best fit. And that's kind of the slope that we are looking for. But again, those differences are called residuals. And the idea is to minimize the residuals. So if they're all falling right on the line, then you have no residuals. And that means you have a really good model. So really what we want to get out of regression, and the reason I like this tool quite a bit, is that it gives you a way of coming up with an equation. And once you have that equation, you can do a lot of good things with that. And it kind of helps understand the model of what's going on. And everyone kind of remembers this y equals mx plus b from grade school, and the rise over the run, and that type of thing. And this is kind of the foundation of that. So we're going to come out of this with an equation, and we have a slope, y-intercept, and a slope, and a variable, and an output. And that's the same structure. And then we add in more variables. We just add in different slopes for each of these. And this could go out to 4, 5, 6, 7, however many factors that you want to have in your model. Okay, so that's kind of the foundation of what your equation is going to look like. So that should be pretty familiar to you. So going back to the housing example, we have the simple regression model is just one value, the output, selling price, versus one variable, square footage. And you see when you do the analysis, you end up coming up with an actual number to apply to that. So this $122 says that's what the value of the house is. For every additional square foot you add, you get $122 in value to the house. And then they might have some constant value, which is the intercept, and that says it's $37,000. And that's kind of just to offset some of the equations. So sometimes you'll see these equations come out and they're pretty representative of what you would expect. And other times it doesn't quite make sense. You'll look at it and say, that doesn't, the equation works, but intuitively it looks like it's adding value when it's subtracting, and it's subtracting when it's adding. So you get some pluses and minuses that don't always work out. So that's something you'll kind of have to work through too, is you can get an equation and sometimes it really matches perfectly and other times it doesn't look like it matches. But the end result gets you the answer you're kind of looking for. So it's good to kind of look at some of these things and it helps you understand it a little bit. So when you add more variables down here in multiple regression, we added in the lot size, bedrooms, if there's a garage, that's a kind of a yes or no. We'll touch on that briefly. And if it has central air. Actually, I'm sorry, the garage is actually a size, and then the central air is a yes or no. Does it have it or not? So then we come up with a little more complicated equation, but again, you can start to see the relationship on some of these variables. So each bedroom is about $8,000 added to the value. And if central air is included, then there's additional $5,000. So you can start to now compare some of these variables and try to understand how they influence what you're trying to look for. So then you can get a little bit more accurate information. So here we had predicted about $230,000. Maybe with this additional information, we get a couple more $1,000 lower and maybe a little bit more accurate than what we're getting. Sometimes that could be a lot bigger difference depending on how important the variables are. So that's kind of the, one of the key things you want to understand is you can always get out an equation using regression. The question is it any good? So we want to have some way of determining is it a good equation or not. So if you had different variables, let's say you have a house that you're building and you want to predict what it cost if I sold it, and you plugged in the information and what you actually sold it for was exactly what the model said it would, then that'd be a perfect equation. You'd have no difference between what it predicted and what it actually was. So that's kind of like 100% of the factors contributed to what your answer was. Okay, you're not going to get that in reality, but that's kind of the concept behind this R-squared value that comes out of some of the analysis. And I'll show you an example a little later. But that's kind of what you're looking for. It's kind of between a 0, it's not helpful at all, it doesn't tell you anything about your results, all the way to 100% would be it's perfect. Every time it gets the exact value you're looking for. So it's somewhere in between there, and that's kind of how you're judging it. So if you had something that was a 0, you said you might as well just pick the average because adding these other factors in isn't going to get you any more information or any closer to the real result you're looking for. So it starts to tell you that, okay, I'm on the right track, or I'm not even picking the right variables at all, because that's kind of where you're starting from, is you got this open slate of, well, there's lots of variables to pick from, which ones do I start with? And everyone kind of logically starts to identify some pretty important ones, but you start getting into it, it's, okay, how far do we go? How many more variables do I need to collect? So this information can help you understand, are we getting close enough? Are we getting a good model or not? So here's what R-squared value looks like. So in the upper left, you can see we have 11%. So that's probably not very good. If you're looking at 0 to 100, 11 is not very good. And if you look at this line, this black line is that equation. It says this is what you would predict for this. And then the blue dots are what actually the results were in your data. So you can see that if I was predicting, let's see, 2,500, I would predict it around, this example, about 400,000. But in that case, it was actually 1 million. Oops, that's pretty far off. So that's not a very good model. You can kind of see that because the lines don't really match up closely with the data points. Now this one's a little bit better, so we're at 64%. You can see the line is a little bit closer to the data points. So if I do predict a value here, say the 2,500, now it's saying, no, it's more like 325,000 in reality. So there's still a difference there, but it's not quite like 1 million like we had before. So, and then as you see, as we get better and better R-squared values, these data points start to get closer and closer to that line. And so we're reducing down what was the term I mentioned earlier? Residuals. Right, so the residuals are much smaller. The difference between the dot and the lines are much smaller, and that makes it a better model. And then here is a really good model, 99.9%, where you can see the data points are pretty much right on that line. It's about as best as you can get. So that means it's really predicting exactly what you're going to get. So here's at 3,500, you're getting exactly $300,000. And the difference is very minor. So if you have that, you can be very accurate on what you think is going to happen. Okay, so let's take another example. This is a pizza delivery, and we want to compare the difference between in wait time. So you order pizza, how long is it going to take for you to get one at your house? So the wait time is in minutes over on the left here. Low is 35 up to 55 minutes. And the deliveries are across the bottom. This is the number of deliveries that are coming into the store. So you can see that when we have a low number of deliveries, our wait time to get the pizza is pretty low. And then as the number of deliveries start to pile up, our wait time starts to go up. almost an hour the pizza or more. So now we can put an equation to that and actually come up with an answer for it. So this is a fitted line plot, but it's basically just a regression with one factor in this example. And what we come out with, it provides us with this equation. It says the wait time is 32 minutes plus 0.58 times the number of deliveries. And you can see with the R squared value, 94%, that's a pretty good model. That means we're pretty accurate with this information that we're using. We can get pretty close to predicting when that time is. So if you can look at how many orders are coming in and say, we got 25, all right, you better tell the customer it's going to be about 50 minutes before they get their order. Okay, so now you are able to take some of your past information and turn it into predictive information going forward. So it's not, oh, it's going to be between 30 minutes and 60 minutes. No, you can start to get very accurate. And then you're starting to set very specific expectations for your process. We'll touch on that a little bit later here. So one thing we tried to look at, when I lived in Melbourne, Florida for about 6 years with Rockwell, and trying to do a little bit more with energy and trying to look at how can we use our data to reduce our footprint as a company. So one of the areas we want to look at is our energy and specifically electricity usage. And so we gathered up the kilowatt hours by month over a couple, I think this is a 2-year period here. And the question was, well, what drives the electricity? You say, well, we've got, how many hours people are working, and we've got the types of equipment we're running, and how many employees are there, maybe the amount of product that we're building. So there's some, generic factors people are throwing out. What other factors can you think of that would affect the amount of electricity used?
Air conditioner.
What's that?
Temperature.
Temperature, outside temperature? Okay, yeah.
The air conditioning cost.
Yeah, so seasonal. You can see in the data it's not consistent month to month, right? So there's something that fluctuates up and down, and that seems to match pretty close with August, June, July, August, both years. So looks pretty safe that we could say that the outside temperature has something to do with our electricity usage. But there's other things. It's not really perfectly aligned with that, but we can at least start with that. So simple regression, let's just plug in a variable that we think is pretty important, and that looks like that would be the first thing I'd start with too. Something seasonal. So what kind of data represents seasonal?
Heating and cooling degree days.
Degree days? Okay. We didn't quite go that detailed yet. You're a step ahead. Sorry.
Maybe average temperature?
There you go. Yeah, so we used, we gathered average high temperature and average low temperature as a starting point. We ended up finding out they're pretty much correlated directly with each other, so we really only needed to look at one of those variables. So we plugged in temperature. We did a simple analysis, and it came up with an equation, and we plotted that equation. And so the red line is the prediction based purely on the temperature outside. And you say, hey, that's kind of starting to match up pretty good. That's a lot better than what we had before. We didn't really have any way of predicting. We would just take an average across the year and say, that's what you're going to get month to month. And the first couple months you were over your usage, and then a couple months later you were under, and then you kind of just waited to see at the end of the year how it ended up. You really had no idea what was going on. Are you using more than you're supposed to or less? So really not really understanding the data. And this is kind of the first step to try to understand that. So average high temperature starts to match a little bit. Yeah, there's some gaps there. It looks like we don't quite understand exactly what's going on in the summer. It's not perfectly lined up, but it's not too bad. It's a lot better than what we started with, which is very little. And we get a number, an R squared, so about 50%. So say, okay, not bad, but we could probably do a little bit better. Like to see those numbers in the 70s, the 80s. So we're really starting to get a lot more accurate picture of what's going on. So we start talking about what are those other factors that influence that. And maybe we look at some of those gaps and say, what is happening in this? Why is it so far off in these areas? And those are some of the things you can do to try to help generate ideas about what are the right factors to look at. So I kind of mentioned a few of them before. We looked at spares, number of spares that were produced, because that's a part of their business, and the final product that was produced, how many of them we produced each month. Maybe that has something to do with the amount of equipment we're using. We also looked at how many employees we have. So maybe that, if we have more employees, we have more computers, we have more maybe lights coming on, we're using up more, even more electricity to cool the areas. Also looked at working days. So one of the things that we looked at on the bill was, it's the same time of day, or the same date each month, but how many working days were in that month, in reality, might influence our results. Well, some months we only had 15 working days, other ones we had 22. That probably has something to do with the amount of usage we had. So we brainstormed some of those ideas and plugged them into the model. So basically we went and tried to go back to those 2 years of data and go back and gather that information and plug it in and see which ones come out and which ones are important, which ones are not that important at all. So with this one, we ended up having, I think there's one more slide here. Yeah, let's go to this one. So the R squared improved quite a bit to 76%. So now, and you can see the picture is much better. Not perfect, but now we're really getting pretty accurate. And then we have an actual equation that gets generated. This is we use Minitab at Rockwell. So this is an output of Minitab. So it says the usage is some set amount, and then a certain factor for the temperature outside. Average high temperature is what we end up using. And then the other one that was important was the spares. It wasn't the final product that we built. It was the spares and the smaller components that actually was a better predictor for, maybe it was the amount of machine or equipment that we used, or maybe it's the amount of labor. It could be a lot of different things. And employees did come into that equation. So the more employees we have, the more electricity we're going to use. But stuff fell out too, like the working days. So we would fluctuate between like 15 and 22 days a month. But that didn't seem to be important to the electricity usage, which I thought was really unusual. We had a 9/80 work schedule, so every other Friday was off. So that's why it was say 15 days. Some months we'd have 3 weekends that we didn't work on those Fridays. So that started raising other questions like, well, why isn't that important? Why wouldn't the number of days where you have a full labor in the facility not influence your electricity readings? Significantly, at least. And then what is, how do we deal with stuff like an average high temperature? So okay, that's a factor. So now what do we go do? Move the facility somewhere cooler? Try to save electricity? How do we convert a factor like that into action or into an improvement of some sort?
Insulation, more efficient motors on the HVAC equipment and stuff like that.
Okay, so what does the high temperature do to the facility? Yeah, you start running the air conditioner. So when are we using the air conditioning and how efficiently is that being utilized? And is it being run all the time or is it just when people are there? What are the settings on the equipment? What's the power ratings and the efficiency of the equipment? It starts asking questions about not, oh, we need to stop hiring employees, but what are we teaching or promoting to our employees that's influencing this number? And how can we maybe make their impact less by looking at the things that the new employee would add to that electricity? So it's not about looking at this and saying, well, we can't affect that, can do about it. What do those things influence that we can do something about? And that's employee education, and it's looking at the system as a whole. And this one we probably maybe wouldn't be able to do a whole lot, but maybe there's certain equipment that gets run to deal with those spares. And maybe we need to look at, is that being managed effectively? Is it running efficiently? Is it being left on all the time? And maybe we could shut it down. So you start asking additional questions to see if these are the most important things I can focus on. These are the ones that are going to have the biggest bang if I can make an improvement there. So it allows you to take this unknown of, I don't know where all this is coming from. We don't have the metrics to try to figure every little piece of it out. We don't track individual employee electricity usage. But here I can at least start to take this information and now focus on a couple key things. And I'm not going to work on the working shift differences there. It didn't fall out as a critically important item. So an example like this is good because we also did one in a Cedar Rapids location, and all we needed was the temperature. That was a like 80% predictor of electricity. And everything else is just very minor. So we could only really had to focus on that heating and cooling aspect of that building because that was going to be our biggest benefit. So we looked at, how old's the equipment, how is it set up, what are the settings, all that stuff. And so without knowing anything, without having detailed measurements on every single equipment that we had, we were able to just quickly figure out, okay, that's where our focus will be. So it allows us to take some information that's unknown and now fairly easily, especially like temperature, that's easy to gather and collect. So now we can make some quick decisions and determine some priority. That was especially like electricity, that was a big thing with Rockwell. You're familiar with our C Avenue location, so I think it's like 2 million square feet. And you're going to get basically an electric bill like you get at home. That's about the detail of data we have available. So where do you start in that kind of a building? And so some of the stuff in this approach is where we started to look. I was trying to identify some of those variables. Okay, when I first started, I got called in, and I got hired in as a statistician. That was my undergrad. And one of the first projects I got assigned to was Boeing wanted to do some stuff with supplier part modeling. They wanted to do some predictive things with how do we look at quotes on circuit boards and see are they providing us a lot of different factors that go into each design, so it's hard to compare one-to-one to each other, but maybe there's some general trends about each circuit board we can look at and see if there's a model that fits that. And then look to see how far off are some of the quotes we're getting back from the supplier. So put me on this nice 747. I was up in the second floor of that aircraft. I was like, this job is pretty nice. This is all right. My first company flight I took, and first class upstairs, and pretty much wine and dine, and it was pretty nice. That was the last time I ridden first class for the company, but things changed quite a bit after that. But so that's what they were looking at and what we did is end up gathering a lot of data from different drawings that we had. So we had a couple people go and pull drawings and go through manually and record down information. What is the price? How many layers does it have? Number of boards, number of panels, all these different variables that they thought might be important predictors of the price. So what we wanted to do is try to figure out how do we get this down to something, the really important stuff. And then do we have all the right variables or not? So one of the two other variables I'm going to just touch on real briefly is, I mentioned before, like a yes or no factor. That's called a dummy variable, but basically we convert the yes or no into a 0 or a 1 in the data. So if it has that condition, so if this one was gold-plated, yes or no, then a yes got a 1, and if it didn't, then it got a 0. Same with this material type. You said, does it have this FR4 material or not? Okay, so that allows us to take a variable that, a lot of these numbers are numeric, or continuous variables. When we use regression, this is primarily what we're dealing with. But we can also take advantage of some categorical type variables if we can convert it into the situation. So put this all into the model, and there's a lot of stuff that goes into coming up with an equation. So I can throw all the numbers in, and I can press, regression, and I can get a model that comes out. But there's a lot of work to kind of set that up and make sure that, does the data look right? Do I have any strange readings in there? Did everyone type it in correctly? Especially looking at hundreds and hundreds of records, it's easy to overlook some typos and errors and stuff like that. So there's a lot of graphical things that you want to do and a lot of assumptions you have to kind of review to make sure you really got a good model. But you can pretty easily get an equation out. The question is that really a good model, and do I want to go make some major decisions off that right away without a little bit more investigation? So there was a lot of stuff that goes on ahead of that. But the end result is we were able to identify some important factors. So the ones in red are the significant factors for the model, and there was two other ones that are kind of marginal. If you remember with p-values, you're trying to look for stuff that's less than 0.05. That means that there's a very small chance that you're going to see a factor like that was just randomly happened to be very influential. So it's more likely that this is a very important factor. So we had taken out the ones that were not significant out of this analysis here. But as you can see, now we come up again with this model, and you can see that here are the ones that are important, and there's other ones that aren't on there that we took out. They were not important. I think the number of holes per board or something like that was not important. And then, okay, so this is a key thing to look at. We're at 72% for the R-squared, so not bad. It's probably got a pretty decent handle on it. Like I said, that 70–80% range is not too bad for a model, especially something as complex, and I'm sure a lot of different other factors you could look at. So that's where it gets a little tricky, is where do I stop? If I could look at it and say, okay, I want to be at 90%. What other data do I need to go gather and include in here that might explain it? And so it really just kind of depends on how accurate you need to be, what is the intent of the model that you're using it for. But this really helps you get a feel for how good is it. And I think that they were saying, that's pretty good for a first start at this, is for 72%. Like we kind of are getting close here. And now we can take this, when something new comes in, you plug these numbers into your equation, and then now you have a prediction for what that should be. And it's not going to be exact, but it's got some kind of some range around there. So this is what this particular one looks like. And the numbers are skewed a little bit. That's not the actual number on the price. But I want to just show you the picture here. As you can see that, so if I predicted this over here, then the actuals were somewhere in here, not too far off. It's a decent model. So then I can look at some things maybe up here and say, okay, is this just variation in the model, or is this maybe a particular supplier that always seems to be running a little bit higher on all theirs? If I plotted just a certain supplier, maybe these are all their quotes that come in. Then you start saying, well, why are they so much higher than what we would expect them to be? Or maybe we have some suppliers that are consistently down in the lower part of this model, meaning they're always under what we'd expect to have for the actual cost of the boards. What are they doing differently? Is that does that end up being the true cost? Do they always come back later and want to raise it? Or are they doing something different with their processes that make them more affordable, and it's not impacting other things like quality and that sort of thing? So for them, they were encouraging us to use it as a tool to try to identify how people related, and that you have some kind of an idea of what the price is going to come out to. And then you can kind of look at it and say, if it's really far off from this line, why is that? Is there something special about it that we didn't come into our equation? Okay, so what are other applications? So giving you a couple generic ones and then two specific Rockwell ones. If you're looking at something like baseball, the number of wins that a team gets you could run the numbers and figure out that the earn run average and the number of saves are big predictors for how many wins they're going to have. Okay, so that's an example of a multiple regression. So if you were owning a baseball team, you might want to invest in your pitching and your closer. How about supply chain? So recently we were working on something with shortages and trying to predict, how likely are we going to have a shortage based on quality of supplier, maybe the complexity of the part, whether it's an international supplier or domestic. So looking at some of those things and trying to figure out what really drives it. And the example around that one is a lot of people had ideas about that, and we developed risk scores and ideas around here's what we think might lead to shortages, but we don't really have any numbers to back it up. There's just a lot of gut feel and a lot of experience-based thoughts around where we might have problems. But this allows you to kind of get to a point where you actually have some numbers to back it up. You know what? It sounds like it's intuitive. The number of working days in a month, that sounds like that would be important, but the numbers don't back that up. And that might be another whole other issue. But at least we can have something tangible to talk about versus it's, then you start arguing with people, it's my opinion versus that. Here's what the numbers say. Now you can have a little bit more focused discussion. Environmental thing, how much sulfur dioxide gets put out? Well, that's population of the area, amount of output from some of the key manufacturers in the area, the power plant, and the type of power plant that it is. I think it's whether there was a power plant in that community. And then the type of power plant that it generated. And those are predictors of the amount of sulfur dioxide that gets emitted out of that, into that area. Or a personal thing, how much is my used car worth? Depends on mileage, color, rust, scratches, the manufacturer, the type of vehicle, some features like leather, that type of thing. So what else? Give me a couple different ideas. Anyone have some experience they want to share or an example where they've applied it? And, yeah.
We use it to kind of predict what customer satisfaction scores might be on our surveys for the call center based on are we in the disconnect time period of the year where we'll disconnect customers for their electricity or not, number of outages, and how many employees we have. Those tend to be some of the main drivers there. If people's power is out and they have to wait a long time, they're not very happy.
Cool. Any other examples?
When I was in the Navy, we used it to predict maintenance man hours required for aircraft flight out.
Okay. So
Type
you
of
remember some of
aircraft
the
and flight hours.
variables that went into that?
Yeah, like type of aircraft and flight hours to determine your predicted number of maintenance man hours
that you're gonna
to
need
maintain
for-
the aircraft.
Oh, okay. All right. Cool. Yeah.
In laboratory accreditation, you they have what they call laboratory comparisons. So you take a sample batch and give some to one lab and some to the other and see how close you come with the comparison of means.
Okay.
If they're apart, you know that the samples are from the same batch, so there's probably something that one of the labs is doing incorrectly or not precisely as they should. And so then you go back and look to see what needs to be improved and then test it again.
Okay. Cool. Any other examples? Or any other ideas of maybe just sitting here thinking about stuff and you might be able to apply it where you're working at today? Think about it later tonight.
Is your baseball from Moneyball?
Actually, ASQ had something in the magazine this month on that, and I think that was one of the things. I don't know if it was number of wins. I think it was more like logistic regression on whether they will get to the World Series or not. Was determined on saves and ERA. So that's a good one you might refer to in the quality progress this month is the one on the baseball. So they kind of touched on some of those things, and it's a little bit different regression, so I didn't want to use it there, but. Yeah, there's a lot of good applications. Okay, so going forward then, a lot of you have to deal with some kind of result or output of a process. And that's kind of the response you're trying to predict. If you can predict that, then you can understand how to improve it and control it. So that's really the key. So you first kind of understand what is that output or what is that measurement that's most important. Then you got to go through and kind of brainstorm what drives that, what affects that, and that's where you get as many different viewpoints involved, and how are they going to influence that, and can we gather information about it, or is there some other variable that kind of relates to that we think would get at what we think is happening. Then you have to go and gather data, and most of the time it's not available to you, and you have to go get it manually or physically, go gather it, start collecting it from some point in time going forward. If it all came in this nice database dropped in your lap, that would be amazing. Never that case. So that's the hard work part of this that you can't really get out of. And then there is a lot of this validation and cleansing of that information. So like I said, you can always get an output, but you want to make sure that you don't have the typos, the outliers, the bogus numbers. They captured the wrong information than what they thought it was going to be. So there has to be some sanity check on that information. Then there's a process to really kind of look to see, do other factors influence, are basically saying the same thing in your data. So I mentioned we looked at the high temperature, and we also gathered the low temperature. They pretty much were hand in hand. As one went up, the other one went up. So it really having that extra variable didn't do us any good in the model, so we just took out one. So you do some of that check, and you can do that simple scatter plot I showed you to see if there is a strong relationship between your inputs. There's also some assumptions that I have to look at, some things with normality. I don't want to get into that too much, but then you run your analysis, and it's going to tell you which ones it feels as most important, that really influences the output, and the ones that don't influence it at all. And so we start to whittle that model down to the really important ones. And then there's some analysis. We look at the residuals. So what the pattern of the residuals tells a lot about how good your model is as well. And there's a whole analysis you kind of go through to see if it's, looks like a normal distribution, if it's consistent across all your readings, and are there any big trends or changes in the output over time. So those are some of the assumptions that come into play. And then try out your model with some new information. So you've got a new set of data, and plug it in and see how well does it do. And if you get pretty close, maybe we got something we can use. And if it's pretty far off, then we have to go back and figure out what didn't work very well. Did we really, maybe our data set was limited, it wasn't as broad as we were trying to apply it to. So then there's a bunch of other stuff that comes into play where it gets a little bit more complex, and even this I have to go back and pull books out and kind of remind myself what these mean, and that's where some of the complexity gets in. So that's where I would try to seek some help before you go and present to your CEO or your high-level manager with the results. Have somebody kind of do a sanity check over, make sure it looks okay. The numbers kind of look appropriate for the type of data. If you're having an R-squared at 99.5%, most people are going to say, let me look at this a little bit closer. I think there might be something wrong there. So just have someone at least do a check, and then they can kind of help you decide, yeah, it looks pretty good, or let's back up, and before we do any major decisions, let's revisit this a little bit more. Help me understand what you did together. But I think the real key thing we try to harp on is just try it out. Get some experience with it. See if it works. And then as you do it and you apply it to information that you understand and it's your process or your data, it's going to make a lot more sense than talking generic stuff about a process that you weren't involved with, and you kind of you're not really sure what it actually is doing. So, but when you have stuff that you are familiar with and you can plug it in, now it'll start to make some sense. Oh yeah, that's obvious. I see why that number's higher than that one, because this is way more important than that one. And there's some, just makes more sense to you what you're looking at. Okay, questions? That's all I had. Dick?
Yeah, do you have a statistical analysis for outlier points, or what they call maverick points, to see whether it should be kept with the data or discarded?
This is that VIF variance inflation factor. So, and I don't know all the details how it factors that in, but basically it's looking for data points that if you took it out, it would change the model quite a bit. So it's saying that this is it's driving a lot of the results, and it basically is kind of looking at how many standard deviations away from the average are you. And those are good ways of identifying that, okay, is this really a valid data point that we need to keep in, or is it, there's the typo we're looking for. So that's one of the steps, first thing to look at is how many of those points are there, and there's always going to be some list of them. I'm looking for the stuff that's 3, 4, 5 sigma outside of my model, and that's probably something's going on, or there's a unique situation that kind of explains that one thing. So do I want to include it or not? Is that really representative of what I'm looking for? So that's probably the one I'm most familiar with. Anyone else have a comment on that? Or visually, the graphing of the data points up is another part of this up front. Cleansing through that, so that's making histograms of the data set, and if you see those readings way out, then you can find some of those visually as well. Is there another question? John?
Explain to me homostochasticity.
Nope.
I have not seen that.
Yeah, I think it has to do with the variation across the data set. Is it pretty stable or not?
Okay.
Yeah, it's a fancier word for that.
Or as you go up one side, is it?
Yeah, it's like the numbers get higher, does the variation increase or decrease, or is it pretty consistent across the whole data set?
Okay.
I think that's what it is. I'm not, I threw in some pretty tough ones, just as kind of example, that it does get pretty complex, but there's a lot of simpler the concepts. Don't let that scare you off from getting started or trying something out. Yeah, Karen.
Susan had a question.
I was wondering how much data you had to have before you could rely on the results that you were getting. I know the more that you have, the better it is a predictor, but what's the minimum amount you can get away with and reasonably expect for it to, the correlation to be reliable?
Yeah, that's a good question. I know what the recommendation is, you need to at least have more data points than you have factors. So that's a simple thing. So if you have 10 factors, you need at least 11 data points. But I think I've also heard you want to have 2 to 3 times the number of factors. So for 10 factors, you want at least 30, 40 samples in your data. So you at least have multiple measurements. You're not relying on that one measurement of that difference. Yeah, I don't know if there's like a minimum per se that, if you don't have this, it's less reliable. I think it factors into the variation in your model, and your R-squared won't be as high if you have a small sample size.
Yeah, the reason I'm asking is because I once looked at a presentation where somebody had 2 data points and tried to say it was reliable. And
It's
so
a
I
perfect
just
model.
walked out of that and
Yeah.
say,
That's almost
that's really not realistic.
Sounds
Yeah.
like an interesting project.
Brian, and so you're standing behind the center, and he's going to hike the ball to you
Okay.
in a Big Ten game. What's going through your mind as a statistician as far as key characteristics of whether that punt's going to go the distance you want it to go?
The factors I worried
You
about,
does that actually go through your mind?
it didn't at the time, but I wish it had when I was playing. It worked really well at the field goal kicking with the goalposts and the variation and capability and stuff like that. That's, going back, I wish I would have realized that opportunity to apply that to field goal kicking. But the factors are weather and wind for punting, for sure. So yeah, the stronger the wind, the more it's going to move the ball when you try to drop it, and it's going to affect the snap and where it goes. So you're going to get, you're standing there, and if you have to move, now you're kind of getting out of your rhythm. And if it's rainy, the more slippery the ball. So is the snapper going to give a good grip on it, and am I going to get a good grip getting it? And those are the kind of the main ones, is the weather factors that are the unknowns going into it. So, and then there's the pressure piece of it too. It was always some pressure, but certain situations more than others. Yeah.
How fast is defensive?
I guess if the history of the other teams blocking ability. Punt block success was also a factor, yes. And the return man. So if that person was very good, that was another thing that was in your mind as you're not just getting rid of it and kicking it away, but where are you placing it so it's not easy for them to return it. So it's a lot of the core stuff is feel pretty good about. It's the stuff that out of your control that makes it more difficult.
So do you actually get to watch the game, or do you?
Do I analyze it?
Yeah.
No, I do watch it. I don't get into the Moneyball type of detail, which is, it was a fascinating movie, but yeah, I don't get to that level of detail. It would be interesting to kind of do that with. I have a lot of ideas about it, but it's a lot of work too. Any other questions? Okay, I hope I gave you some good ideas of things to think about and didn't scare you off with it. Again, once you have, the thing I really like about it is it allows you to have this understanding of what's going on in your process, or with the data you have, you feel like you're more empowered to do something with it versus we don't even know, and it's hard to figure out. Well, you can kind of apply some stuff, and it's fairly easy. You know, if you have a software, it's fairly easy to put this in and get some results out of it. So I know Excel has some regression